So I actually had to change the platform. I also had to change to re-record this multiple times. So this is, I think, the fourth time I recorded, starting from this slide. Yeah. So let's go back to user space and basically user space threading and talk about stuff that is actually included in three easy pieces. Uh, so if you basically if we basically start with a threading example, this is how you actually create user level threads using pthread.h, which is the POSIX compatible library. It's also the threading library you would use in C. And you use function pointers, C function pointers, to create threads in C. I hope that you have used them before. um, I am going to, as I said, basically try to have a couple of lectures on C++, and I will try to touch upon some of these things and see if you do not know them also. So, yeah, so this is a very simple threading example where you basically create two threads, P1 and P2, and pthread create is the function call that you use to create threads. So, and you pass in the pointers and you pass in the name of the function, my thread, and then the arguments, which is A, the arguments, which is B. And then you have, uh, sorry, and once you create the two threads basically will, I mean, will run the code that you have in the function pointer. The join statement, as we said, allows the parent process to make sure that to sorry, the join statement is used to make sure that the parent process does not exit before the child processes finish, basically. So it needs to wait for the two processes, P1 and P2, basically. Two threads. Sorry, threads. Um, yeah, and then once you're done, you print end, and then you basically return. Now, this code runs three threads actually, not just two, because you have the parent thread, which is a thread, and you have the two threads that we just created. So there are multiple possible sequences for this code to run. Okay, and these are three threading traces that we can look at. Well, you basically start running. Okay, you print main begin, you create thread 1, then you create thread 2. Okay, and then you basically, if you look at this code, once you do the two creations, line 15 and line 16, you start line 17 is just a comment, so it's nothing. So line 18 is basically when you wait for thread 1 to finish. So you create the two threads, and then you wait for T1. Thread 1 runs now because you're waiting for them, runs print A, returns. Wait for T2 because this is the next statement, and then runs for thread 2 and print B and returns. Okay? And then this is the second trace that you can have. Basically, start running, print main begin, create thread 1, and now once you create thread 1, maybe the scheduler will just decide that, oh, I'm going to run I'm going to run thread 1 right away. The main thread has been running for way too long now, and I need to schedule something in else. So thread 1 starts running right after creation. Then you create thread 2, I mean, you go back to main, and then again, for some reason, well, probably the main the main thread has been running for way too long before you did all of these computations, so it's out of quota when it comes to round robin or something. It's at the lowest level of MLFQ. I mean, for some reason, you basically create thread 2, and you right away run thread 2. Scheduler basically right away, once thread 2 is ready to run, it starts running, basically. And then you wait for T1. Well, there's nothing to wait for because thread 1 is done. Wait for T2, nothing to return to wait for because T2 is done, and then you print main. This is the second possible sequence. Then there is this sequence, start running, print main begin, create thread 1, create thread 2, and then for some reason scheduler decides that thread 2 now runs, and then you wait for T1. I mean, because this is, you basically, once thread 2 is done, you go back to the main thread. The scheduler basically decides that it should schedule now the main thread again. So the first thing that the main thread will do is line 18 in the code, which is basically the join statement. So it joins and it runs print A, because now this has nothing else to do. So it runs print A. Once it's done, it goes to the next statement and basically prints end. So threads are very useful, but they are very problematic. Let us look at example when you're actually doing threading on shared data. In this example, we are going to add 10 million to a counter, to basically a variable that is static. So you have static volatile and counter equals 0. If you jump to main, if you look at main, which is in the box, you again create two threads, P1 and P2, T1 or T2, call them whatever. You print main begin, okay, and you print the initial value of the counter. You create the first thread, you create the second thread, you run join, and once you're done with once both child threads join, you basically print F and print the final value for the counter. Now looking at the thread code, the pointer code basically up there, you have void pointer my thread, and you pass in the arguments. You print which thread is running now. You have an iterator which is I. You iterate over I until it reaches 10 million, and with each iteration you add to counter 1. So counter equals counter plus 1, and then you print when that thread is done. Once that thread is done, you compile that code and you run it. What you expect is that you will see 20 million. So first, in this run, you have main begin counter equals 0, and then A begin, B begin, A done, B done. So basically A starts, but then A has to add in 10 million to basically iterate 10 million times. And this is a lot, so the scheduler basically decides that now it's time to, using the timer interrupt, that now it's time to run something else. It picks B, it runs B, and B again starts doing the counter thing. So A is counting, B is counting now, and then A is done, and then B is done, and then you get 20 million towards the end. This is what you would expect, right? But if you run it multiple times, you might actually find very weird results. Like this one, for example, the summation is not 20 million, it's actually 19,345,000 and some change. Okay, you run it once more, the result changes again. This is obviously problematic. Computers are supposed to be deterministic. When you run a calculation, you want the same answer every time you run this calculation. The problem is the uncontrolled scheduling. You basically do not control when the scheduler kicks in and decides that it's basically moving, removing some thread from the processor and scheduling some other thread instead, or some other process. This sounds like a very simple operation, though. You're just adding 1 to a counter, right? But in reality, it's not. In the x86, okay, and we are not going to go deeply in the details of how this is implemented as an architecture. The way that the x86 works, okay, is that you're moving. So you have the counter. This is 0x8049A1C. This is basically the memory location where your counter is stored. So this is your counter. Okay, as you move the value in your counter into EEX, the register, it's a register called EEX on the processor. So you move that, the value, whatever value is in the counter, to that register on the processor and the hardware, and then you add 1 to EAX, okay, and then you move EAX back to the counter variable. So the way that computations are done is that you basically move the value from the memory or from the cache or from wherever into a register in the CPU. You do the computations and you move the computations back from the CPU to the memory location. Okay, so let us look at what happens if we basically with multiple different scheduling things basically. Okay, multiple different scheduling not policies but multiple different scheduling decisions. Sorry, decisions is the right word. So you have the operating system that has the interrupts, you have thread 1 running, and you have thread 2. Okay, and this is your program counter, your EAX register, and your counter variable. Okay, and this is what is done after the instruction, after each instruction. So thread 1 starts running, and you do basically move 0x84991A1C, the hexadecimal number, this hexadecimal memory address to the EEX register. If you look at the first line, EEX was 0 and counter was 50. But now when you do the move operation, EEX becomes 50 also, and the counter is still 50, right? And the program counter basically moves in order to point to the next line in the computations, basically in the code that's going to run. Okay, so you move from line 1 to line 105. Then you do the addition, so you do add hexa 1 to the EAX. So you see now EAX became 51. Okay, still counter is 50, and the program counter has also progressed to 108. And since so now an interrupt happens. Okay, so let us basically take it step by step. Now an interrupt happens, and it saved T1's state. T1's state is basically its program counter and its EAX, okay, and restores T2's state. Since thread code is shared, since the code for multiple threads is basically shared, it's the same code running, it's shared code basically. So you go back to PC of 100 because this is basically where your actual run is, right? So you go back to PC of 100. This is the first line that you're going to run in your thread. It's exactly the same line. Threads are exactly the same code running multiple times. So you have 100, you have 0 in your EEX, and you have a counter of 50. Okay? Because, well, EEX, the previous run for T1, did not save 51, did not get to save 51. Now you move the same memory address, hexa 8049A1C to EEX. So now you have in your EEX, in T2's EEX, you have 50. You add 1 to 50. Okay, you basically add 1 to EEX. So now EEX becomes 51. But now the scheduler does not kick in, and you're able to move EEX back to the memory location. So now EEX is 51 and counter is 51 because of threads 2 computations. Now interrupts happens, timer interrupts happen, and you save T2's state, and now you get to run from exactly where T1 was going to run. And the next line that T1 was going to run is basically move EEX 0x8049A1C. Okay, do you see what's happening now? Yeah, basically you have 51 in the counter, and 51, the previous value for EX was not saved from thread 1. So now, but now thread 1 has no notion of knowing that, okay, thread 2 has done this on the shared variable data. I should basically I should add another one. There is no way for it to know that. So now the counter, after 2 runs, although it should have added 2, it adds just 1, because now what thread 1 is going to do is just going to save 51 into the counter. Okay, so now with this, you actually probably understand that 2 actual iterations resulted in just adding 1. And this is what we call a race condition. Okay, so let us together think about this question. What will data be at the end of these 2 threads? Assume that data is 0 and is on the heap or global before the program executes.